Ever seen a playground with hundreds of kids, all running around in one giant, chaotic space? Balls flying, kids screaming, total madness. That's exactly what your computer network looks like without something called subnetting. It's one massive, disorganized mess where every single device is trying to talk at the same time. Welcome to the world of a large, flat network. So, let's stick with our playground analogy. Imagine this huge field is your network, something like 19.168.0.0 with a 16 mask. That means you can have over 65,000 devices, or kids, in this one single playground. Now, imagine one kid yells, "Hey, has anyone seen my red ball?" In a flat network, that's a broadcast message. Every single kid in that entire playground has to stop what they're doing and listen to that one question, even if they're on the complete opposite side and have no idea what a red ball is. This is called a broadcast storm, and it's a nightmare for network performance. Think about it. With thousands of devices all yelling into the same space, you get massive traffic jams. It's like everyone trying to use the same swing set at once. Your network slows to a crawl. On top of that, it's a security disaster. If one kid gets sick, or in our case, one device gets infected with a virus, it can easily spread to everyone else because there are no barriers. And finally, it's incredibly wasteful. If you only have 500 kids, why reserve a playground big enough for 65,000? You're wasting a ton of space, or in networking terms, a ton of IP addresses. There has to be a better way, right? Of course, there is, and it's called subnetting. This is where we start building some fences. Imagine we take our chaotic playground and we start sectioning it off. We put up a fence here for the soccer field, that's our engineering department. We build another area over there for the swings, that's for the marketing team. The basketball court becomes the HR department, and that little sandbox in the corner, that's our guest Wi-Fi. All of a sudden, we have order. The soccer players aren't running through the sandboxes, and the kids on the swings aren't getting hit by basketballs. Each group has its own dedicated space. Subnetting is literally the act of taking one large network and breaking it down into smaller, more manageable subnetworks, or subnets. Now, when a device in the engineering subnet sends out a broadcast message, like does anyone have the latest code? Only the other devices within that engineering subnet hear it. The marketing and HR teams are completely undisturbed. They're in their own little broadcast domains. This simple act of organization solves so many of our problems at once. The chaos is gone, replaced by clean, efficient, and secure zones. But how do we actually build these digital fences? It all comes down to two key things: the IP address and its partner in crime, the subnet mask. Let's get into the magic behind it. Every device on your network has an IP address, like 190.168, 1.10. Think of this as a kid's full name and their assigned playground section. The IP address has two parts: the network part, which says which playground they're in, and the host part, which identifies the specific kid. The subnet mask is what tells us where the network part ends and the host part begins. It's the blueprint for our fences. You'll often see this written in CIDR notation, like a slash followed by a number. For example, 24 for an address like 190.168, 1.0 to 24. The 24 means the first 24 bits of the 32-bit IP address are for the network, leaving the last 8 bits for the hosts. This gives us 2 to the power of 8, or 256 possible addresses for our devices. Now, here's where subnetting comes in. We can borrow bits from the host part and add them to the network part. This is like making our network portion longer and our host portion shorter. Imagine our fence. The subnet mask is the height of the fence. The more bits we borrow, the higher the fence gets, and the smaller the individual playgrounds become. For example, if we change our 24 network into multiple over 26 networks, we've borrowed 2 bits from the host part. This divides our original big playground into 4 smaller, equal-sized playgrounds. There's a simple formula to remember. If you borrow n bits, you get 2 to the power of n new subnets. And for the number of hosts in each new subnet, if you have h host bits remaining, you get 2 to the power of h minus 2 available host addresses. We always subtract 2 because one address is for the network itself and 1 is for the broadcast address. You can't assign those to devices. So, a longer subnet mask means more networks, but fewer hosts per network. Let's walk through some real examples to make this crystal clear. First, an easy one. We have the network 192.168.10.0.24. Our boss says, I need for separate networks for different teams. To get for subnets, we need to borrow bits. How many? Well, 2 to the power of 2 equals 4, so we need to borrow 2 bits. Our original 24 mask becomes a 26 mask. This leaves us with 6 bits for hosts, so each of our 4 new subnets will have 2 to the power of 6 minus 2, which is 60 to usable IP addresses. Now for a medium one, this is more realistic. We need to create subnets of different sizes. This is called variable length subnet masking, or VLSM. Let's say we need a network for 50 hosts, 1 for 25 hosts, 1 for 10, and 1 for 5. We always start with the largest requirement first. For 50 hosts, we need enough host bits. 2 to the power of 5 is 32, not enough. 2 to the power of 6 is 64, perfect. So we need 6 host bits, which means our over 26 mask. Our first subnet is done. For the 25 hosts, 2 to the power of 5 is 32, which is plenty. That requires 5 host bits, meaning a 27 mask. For 10 hosts, we need for host bits, a 28 mask. And for 5 hosts, we need 3 host bits, a 29 mask. By using VLSM, we create perfectly sized subnets and waste far fewer IP addresses. Ready for a tough one, the challenge. You're given the network 10.0.0.016 and you need to create at least 8 subnets that can each support a minimum of 500 hosts. First, let's figure out the hosts. To support 500 hosts, how many host bits do we need? 2 to the power of 8 is 256 too small. 2 to the power of 9 is 512, that works. So we need to leave 9 bits for our hosts. A full IP address is 32 bits. 30 to minus 9 host bits means our new subnet mask will be a 23. Now, let's see how many subnets this gives us. Our original mask was 16, and our new one is 23. We borrowed 23 minus 16, which is 7 bits for the network part. 2 to the power of 7 is 128, so we can create 128 subnets, each with 510 usable hosts. Since we only needed 8 subnets, we have more than enough. Problem solved. So, after all that math, why do we even bother with subnetting? Let's do a quick side-by-side comparison. Without subnetting, you have one huge, slow network. With subnetting, you have multiple smaller, faster networks because broadcast traffic is contained. Without subnetting, a security breach in one corner can affect everyone. With subnetting, you can place firewalls between your subnets. If the guest Wi-Fi gets compromised, your critical engineering servers are still safe and sound behind their own digital fence. It also makes your network way easier to manage. If there's a problem in the marketing department, you know you only have to look within their specific over 27 subnet, not the entire company network. And, as we saw with VLSM, it drastically reduces wasted IP addresses, which is incredibly important, especially in large organizations. Alright, let's do a quick recap. A flat network is chaos. Subnetting brings order by creating smaller, isolated subnetworks using the subnet mask. We borrow bits from the host portion of an IP address to create more network portions. More network bits mean more subnets, but fewer hosts per subnet. This leads to better performance, tighter security, easier management, and efficient use of IP addresses. It's a fundamental skill for anyone in IT. Now for a quick quiz to see if you were paying attention. If you create a subnet with a 27 mask, how many usable IP addresses for your devices do you get in that subnet? Think about the number of host bits left. I'll wait a second. Got it. It's 30. Our 27 mask leaves 5 host bits, and 2 to the power of 5 is 32 minus the network and broadcast addresses. You get 30. I hope this visual guide to subnetting helped clear things up. If it did, please hit that like button and subscribe for more networking explainers. And for a real challenge, comment below with the toughest subnetting problem you've ever faced. I'd love to see them. Thanks for watching, and I'll see you in the next one.